In this experiment, I'm going to be doing a side chain oxidation on one of the components of anise oil. This is the molecule that has like a black licorice smell. The structure of the molecule that we're going to be working with looks kind of like this, this is anisole. The actual molecule that we're working with has an alkyl group located somewhere on the ring. We don't know exactly where the alkyl group is located, and that's what this notation represents. So this notation that I've drawn here means that we have an alkyl group either ortho, or maybe it's meta, or maybe it's para. We're not exactly sure. So we're showing that alkyl group coming out of the center of the ring. This actual alkyl group here is 3 carbons with a double bond, so it's 3 carbons and 5 hydrogens. And I'm not going to write out the structure of this alkyl group because if you recall, the side chain oxidation process is just going to completely strip it off the molecule. There are a number of different ways that we can actually carry out a side chain oxidation. The method that I'm going to use is potassium permanganate, which is dissolved in water, with a lot of heat. And then I'm going to be following that up with a strong acid. I'll be using hydrochloric acid. And as you learned in class, these reagents are just, first of all, they're going to leave the methoxy group alone. They are going to remove the alkyl group, oxidize it completely to form a carboxylic acid. The first step with just the potassium permanganate forms a carboxylate ion, and then when I follow it up with hydrochloric acid, that's what gives us the actual product. Now, the goal of this experiment is to determine the relative position of the R group, or to determine the relative position of the carboxylic acid group relative to the methoxy group. So we're basically trying to figure out, is this an ortho product, or is it a meta product, or is it a para product? And we'll do that by determining the melting point of the product of this reaction. The ortho, meta, and para products have pretty significantly different melting points, 101 versus 110 versus 185. So it'll be really easy for us to distinguish which isomer we actually have. So for example, if we get a melting point of 110, that's going to tell us that we actually have the meta product, and that means that we started with a meta reactant. There's another ingredient present in this particular experiment. We're also using the catalyst aliquot 336, which I have used before if you've watched these videos. The purpose of aliquot 336, it's a phase transfer catalyst, meaning that it helps bring ionic compounds together with nonpolar organic compounds. This reactant is very nonpolar, very organic. Potassium permanganate is very polar, it's an ionic compound. So the aliquot 336, its role is just simply going to be to pick up these potassium permanganate ions and bring them to the organic anise oil molecule so that the reaction can actually take place. The reaction itself, the actual process in the lab, is really simple, which is kind of surprising considering how much damage is being done to this molecule. So let's just take a look at the actual process, and then I'm going to come back and talk a little bit about the purification and the cleanup of this reaction. We're going to be starting with 0.5 grams of potassium permanganate, KMnO4. This is a really fine powder, and it's also like really brightly colored, so it stains really easily. Even though it looks black, it's actually a really dark purple. So we're actually going to be using 0.582 grams, and I'm going to be transferring it into this little tiny Erlenmeyer flask. And I'm going to do it right here just because this powder is so fine. Carrying it to the balance, I might spill it. And then also in this flask, I'm going to be adding some aliquot 336. Which we've used before. It's like this really, if you remember, it's this really sticky, gooey liquid. And I'm just going to be putting it straight into the Erlenmeyer flask using this pipette bulb. I'm going to be using 0.1 grams of the aliquot. This is a catalyst, so if I get too much in there, it's okay. This stuff is really thick, kind of like honey. we ended up with 0.138 grams. So I'm adding a little stir bar to the Erlenmeyer flask, and I'm going to be putting 10 milliliters of deionized water into the flask as well. This is all going to get dropped down into a water bath. I'm going to heat the water in the water bath up until it starts to boil. This reaction does require quite a bit of heat. Notice a really bright purple color, that's the potassium permanganate. So once this solution gets nice and hot, starts boiling, then I'm going to add the anise oil. The instructions say that I should add about 5 drops of anise oil, but I'm gonna add 10 drops instead. And the reason for that is that 5 drops is a really small amount. This reaction doesn't produce much product, and that makes it really difficult to analyze. So 10 drops of the anise oil will make things a little bit easier. This is just gonna sit and react for 15 minutes inside this boiling water bath. This has been reacting in the boiling water bath for about 15 minutes. This first step of the process has just been to convert the side chain alkyl group into a COO- group. And so what I have inside that little flask right now is like a deprotonated carboxylic acid, basically. It's just a COO-. And what I'm doing now is getting ready to perform the second step of the reaction. The second step of the reaction is where I'm using hydrochloric acid, HCl, to protonate that COO- group to make the benzoic acid. The flask is still kind of warm, but it's not super hot. The instructions want me to wait to let it cool down to room temperature, but I usually don't have the patience for that. I'm going to be transferring this into a beaker. The only reason to transfer it into a beaker is that it's going to make it a little bit easier for me to work with. Erlenmeyer flasks are pretty difficult to work with because of their narrow opening. For the protonation, I'm going to use 6 molar hydrochloric acid. The instructions don't really give me any kind of guideline on how much to use. I'm just going to start with about a milliliter. And what I'm going to do is initially transfer this milliliter of hydrochloric acid into my little tiny beaker and use it to rinse any of that, like leftover. You can see all that leftover purple stuff in there. And then I'm going to transfer that into my beaker. And the reason I'm doing this is because if you remember, this reaction produces a really tiny amount of product. I really can't afford to lose any product to the inside of that little reaction flask there. So I'm going to go ahead and test the pH of this solution using pH paper. I don't know how much hydrochloric acid I should add, but I want to get the pH down to around 1 or 2, so I'm going to look for a red color. This pH testing is going to be a little bit tricky because the solution itself is colored, so it's got that really dark kind of brown color to it, and that's going to be transferred to the pH paper. What I'm looking for is the color that's sort of bleeding away from the brown clump. You notice that it's look at this pink color that's bleeding away. That's the pH of the solution. So it is already really acidic. That means that this step 2 is already done, and I'm ready to move on now to purification in cleaning up and isolating this product. So now that we have formed our product, our next job is to isolate it, purify it, and then determine its melting point. In addition to having the product inside this little tiny flask, we have a couple of byproducts as well. One of the byproducts of this reaction is potassium chloride, KCl. The potassium chloride is formed in the step 2 of the reaction when the HCl molecule is used to protonate the carboxylic acid that we formed. The other byproduct of this reaction is manganese dioxide, MnO2. The manganese dioxide molecule is formed in the first step of the reaction. It's the byproduct of the oxidation process. When the potassium permanganate reacts with the original molecule, some manganese dioxide is synthesized in that step. And then of course we have a little bit of the aliquot 336 that we have to separate as well. That's going to be pretty easy. As we've seen before, it's just really sticky and it just kind of sticks to the inside of the flask, and we can just pour everything away. The product of this reaction is organic, and the byproducts are both inorganic or very polar, so it should be pretty easy to separate the two from each other with something as simple as water. If we rinse this with water, we should be able to rinse away the KCl and rinse away the MnO2. But unfortunately, this MnO2 is not very soluble in water. So that makes it really difficult to just wash away from our product. And so what we're going to do is take that manganese dioxide and we are going to convert it to something that is more soluble in water. We're going to do that using sodium bisulfite, NaHSO3, not SO4. Sodium bisulfite with a little bit of acid, which we already have present. Sodium bisulfite will react with the manganese dioxide to produce manganese sulfate, MnSO4, and water, and a little bit of unreacted sodium ions. So again, there's not a typo here. We're starting with HSO3 and we're ending with SO4. This is soluble in water, so it's very easy to rinse away. And obviously water and the sodium ion are soluble as well. So what we're going to do next is add some of this sodium bisulfite, and we're going to add it straight into this whole entire mixture right here. The sodium bisulfite is not going to do any significant damage to the product of this reaction. It is going to convert all of the manganese dioxide into something that is water soluble so that we will be able to rinse everything away. We are going to be continuing to add hydrochloric acid to supply the H+ for this reaction and to keep our product protonated. It is possible that this could do a little bit of deprotonation as well. And what we're going to be able to do here is actually watch this reaction take place. The manganese dioxide molecule is a really dark brown, so it's really brightly colored, deeply colored, and really easy to see it's present. And this MnSO4 is white. So what I'm going to do is just start adding sodium bisulfite and keep adding it until all of the brown color is gone, which is letting me know that all of the manganese dioxide is gone. Continue adding it until I have no more color, and then I could be confident that this is ready to rinse. Now, one thing that you are going to notice in this reaction as we're doing the cleanup process is there's a tiny amount of product that's formed, like just a little tiny bit. And the reason for that is that we started with a super tiny amount of reactant. We don't need a lot of product in this particular reaction because we only need enough to take a melting point. So you'll see some challenges that I have associated with dealing with this super small amount of product. We need about 1/2 gram of sodium bisulfite. And we need it to be divided into thirds. So what I'm going to do is measure out the 1/2 gram, and then I'm just going to kind of eyeball it into 3 piles that are about the same size. And we divide it, so we're using 0.564 total. And then dividing it into 3 portions. They don't need to be the exact same size. Because all of this will end up being added just in 3 separate amounts. I'm going to add just one of the portions of the sodium bisulfite, one of the 1/3 of 1/2 gram portions, and mix this up really well. Remember that the manganese dioxide, MnO2, is not very soluble in water, so that's kind of the brown chunks that you see sticking to the inside of the beaker, and I'm trying to mush those down into the liquid and get it all mixing together really well. Remember that this reaction between MnO2 and sodium bisulfite needs acid, so I need to be checking the pH as I'm doing this to make sure that the solution is sufficiently acidic so that this reaction can take place. And this is a hard pH to test because of the color of the solution, but it looks nice and pink, so the solution is still pretty acidic. Looks like it's around 1 or 2. The brown color did not disappear, so that means I just need to keep adding more of the sodium bisulfite. So here comes another one of the portions. And again, I'm just, mixing, trying to get those brown chunks smushed. So I'm using oh, look at that color change. Nice. So I'm trying to scrape down the brown chunks off the inside of the beaker. If you can see this, everything is just like really sticking to the inside of the beaker. Some of that is product, some of that is aliquot 336. And with this stir bar, what I'm just trying to do is smash the chunks of MnO2 into the solution. Even though it's really difficult to see, there are tiny, tiny brown specks that are still present inside this solution, which means that it's not all the way done reacting. You want to check the pH again. Remember that this needs to be acidic. The pH is definitely starting to rise. It's not as dark pink as it was before, but it looks like it's a pretty good match for 2 or 3, maybe 4. It's still acidic enough for this reaction to work. And we really can't overdo it with the sodium bisulfite. There isn't any harm in adding a little bit too much, because any excess sodium bisulfite that I add, I'll be able to get rid of during the crystallization and purification process. So even though this actually looks pretty good, I still have one more portion of the sodium bisulfite that I haven't added yet. And so I think I'm just going to go ahead and add that last third just to use it, and just in case there are any really small granules of manganese dioxide that I can't see. This is the last portion. And once I get this mixed in pretty well, and I feel pretty confident that I didn't really need that last portion, so I feel good about this having used up all of the MnO2. I'm going to test the pH one more time, and this time I'm checking the pH to make sure that I still have my product, my benzoic acid product protonated. So I want to get the pH really low again, back down to around 2. I'm looking for like that reddish pink color. It looks a little bit too basic. The pH looks a little bit too high. So I'm going to add a little bit more of the 6 molar hydrochloric acid to get that pH down really low. And again, with adding the hydrochloric acid, there isn't any kind of danger associated with adding too much hydrochloric acid. We are trying to make a carboxylic acid, so having a really acidic pH isn't going to hurt anything at all. To give this a chance to mix in and react. And then I'll do another pH check. I'm sure you can notice all of the yellow stuff that's sticking to that glass stir rod that I'm using. A lot of that is the product of this reaction. It's just stuck to the stirring rod, and it's also stuck a little bit to the inside of the beaker, which is going to make things really difficult in the filtering process. The pH looks really good, and so now I'm ready to move on to the next step, which is going to be to filter this. So the next thing that I'm going to be doing is filtering the crude product. This is going to be really different from normal filtration or recrystallization techniques, mostly because the majority, maybe even all of the product of this reaction is stuck to that glass stirring rod and also stuck to the inside of the beaker. There isn't very much product to begin with, and there's a very small amount of that product that's actually suspended in the liquid. So even though I'm setting up for vacuum filtration, I really don't expect to collect much product during the vacuum filtration process. I am okay with leaving my crude product stuck to the glass stirring rod and also stuck to the inside of that little tiny beaker. I can just recrystallize straight from that exact same beaker. In the recrystallization process, I'll be able to dissolve the product that's stuck to the inside of the beaker, and I'll also be able to dissolve the product that's stuck to that glass stirring rod. So for the filtration process here, what I'm really trying to do is just get all of the water and like the byproducts that have been dissolved in water. I just want to get rid of them and leave all of my sticky product stuck to the inside of this little beaker. It might be a little bit difficult to understand exactly what I'm going to be doing here, but as we watch the video, hopefully it'll make sense. So look at inside that beaker, look at all of my product. It's kind of that pale yellow that's just stuck to everything. And right now I'm not trying to get it out. I'm okay with it staying stuck in there. I'm just trying to rinse everything around. What I want to get rid of are all of my soluble aqueous substances like the KCl and the manganese sulfite, and things like that. So I'm just trying to rinse everything around. And then in this filtration process, I am just getting rid of the water and the other aqueous products, byproducts, and I'm leaving my actual products stuck to the inside of this flask or beaker. So you'll see that I'm not going to try to scrape any of that stuff out into the funnel. I'm just going to go ahead and let it sit inside the beaker. And again, all of that yellow gooey stuff stuck to the inside of the beaker, that's actually the product of this reaction. And what I'm doing here is kind of collecting it on this little metal spatula to give you a chance to see what it looks like, but also the really small amount that we're working with here. Look at this, hardly any product at all, which is what we expected because we only started with 10 drops of the anise oil. We didn't expect to be collecting very much. So again, I'm setting that aside, I'm not throwing it away. We're gonna recrystallize from that, and also from that glass stirring rod, which has a lot of product on it as well. And then we're just going to take a little peek inside this funnel to verify that we really didn't collect anything at all inside the funnel. There's really nothing yellow in there at all, none of our product. So now it's time to do the recrystallization. Remember, the product is just stuck on the inside of our beaker, a glass stirring rod, and also a metal spatula. I'm recrystallizing from boiling water, and I'm starting by just putting the boiling water directly inside that beaker that's got the product stuck to the sides. And I'm using this pipette to rinse down the sides of the beaker to help dissolve the product that's stuck on the sides of the beaker. Then I'm going to be using the metal spatula as a way of stirring, and also this is the same metal spatula that I scraped the beaker with in the last part of the video, so this has got product on it as well. So this is dissolving a little bit of the product off of the metal spatula. I'm scraping everything down, trying to get it down into the liquid. Remember that we don't want to add too much water or solvent during the recrystallization process, so even though I have only a small amount of water in here, I don't want to add more water until I feel like that it's really necessary. Again, using the water to rinse down the side of the beaker to help get everything rinsed from the beaker and dissolved in this hot water. And once I have cleaned everything off of the metal spatula, I'm going to switch to the glass stirring rod to help get everything cleaned off of the glass stirring rod as well. There's quite a bit of product on the glass stirring rod. This recrystallization is a little bit difficult to gauge because the product is kind of oily, so in water it doesn't dissolve super well in water, and it's difficult to see when enough solvent has actually been added. Normally we don't have to do these types of things in the recrystallization process because normally we're working with a large enough quantity of product that it's okay for us to, leave stuff stuck to the inside of the beaker or leave stuff stuck to the stirring rod or to the metal spatula. But in this situation, because we are only synthesizing a teeny tiny amount of product, we can't afford to leave anything behind. It's looking pretty clear. The beaker is looking pretty clean. Like I've done a really good job of scraping everything down into the water and getting everything rinsed. Using the pipette to help further rinse stuff down inside the beaker. What I'm doing here by reusing that solution is a way of helping to clean the inside of the beaker without adding additional water. Now, if you're feeling a little nervous there about how I've used that pipette to suck up some solution and then I used it to suck up water, it looks like cross-contamination. In normal situations, that would be a really bad thing to do, but since I'm recrystallizing, I'm just transferring that water into the right-hand beaker anyways, it's okay to cross-contaminate. And it's important in the recrystallization process to be patient, to give the solution a chance to heat up sufficiently before you decide that you need to add a little bit more water. So that's what you see going on here. I have to be extra careful in this recrystallization because, again, just because of the small amount of product that I'm working with. It can be really easy to add way too much water, and if you add way too much water or solvent during the recrystallization process, it makes it extremely difficult to actually get crystals, to get your product to precipitate out of the solution. Since we have such a tiny amount of product, I really can't take that risk. Every time I swirl the solution or tilt it like this, a little bit of the product gets stuck again to the inside of the beaker, and that's why I have to continue to rinse the beaker down. But unfortunately, you can't stop swirling it or tilting it because you need to be able to see during the recrystallization. You need to be able to see if everything is getting dissolved. So this is going to be enough water. And what I'm going to do now is just set this aside, let it cool to room temperature, and then chill it in ice to help it crystallize. After it's been sitting in ice for a while, then I'm going to go ahead and filter it like normal and let it sit and dry overnight. Our product has been drying for quite a while, and I don't know how well you can tell, but it's like a solid, almost looks like the filter paper here. Like it's dried in this really solid piece that I'm gonna try to keep that intact while I weigh it. I'm gonna start by tearing this piece of filter paper, or weighing paper. We're gonna weigh it out on this piece of paper. And like I said, I'm gonna try to just transfer it out because this is really cool. Like, I don't see it happen like this very often. Look at that, that's really awesome. It just like stayed together in one chunk. So this is a very small amount of product. It doesn't really look like there's anything left on the filter paper. Looks like we got 0.015 grams. So we've got 3 possible products for this reaction, and we're going to identify them based on their melting point. The first possible product has a melting point of 101, and the melt temp right now is at 97 degrees. So if we don't get this melting by, let's say, 102 degrees, then I'm going to ramp it up to the next possible melting point. We're at 99 degrees and still not started melting yet. Our first possible melting point is 101. So now it's 100 degrees and it isn't showing any sign of getting ready to melt. So I don't think that we're going to be melting at 101. When we get close to the melting point, you can start to see it starts looking sticky, it starts kind of shrinking. I don't see any of that happening. Now we're at 101 and there is no sign of this melting at all. The next possible melting point is 110. That's not too far off. So what I'm going to do is pretty quickly increase the temperature up to, let's say, 107. It's at 104, and and still not melting, so it's definitely not the product that melts at 101. So now we're at 105, 106, 107. And now we are heating up from 107. Again, the second possible melting point is 110. We're at 109 and it doesn't look like it's getting close to melting. It almost looked like it was kind of starting to shrink a little bit, but I'm not sure if I just imagined that. We're at 110. And it doesn't really look like it's changing, but every once in a while I feel like it kind of looks like it's starting to shift a little bit. The next possible melting point for our product, so since it's not melting at 110, then that kind of leaves us to the assumption that it is going to be the product, the third possible product, which has a melting point of 185. We shouldn't just make that assumption without testing it. We should actually get to a point where this product melts so that we can verify. We've ruled out that it's not the product that melts at 101, or probably not the product that melts at 110, but that does not mean for sure that we have the correct product. We could have just made something completely random. It's at 111 now, and it's really looking like it's not going to melt. So what I'm going to do now is go ahead and warm this up quite a bit warmer. The machine, I just changed the setting to not really to jump up to a higher temperature, but to increase temperature at a faster rate, because I'm not completely confident that it's not about to melt. So right now it's at 113, 114. The temperature is just increasing more rapidly. And if we get up to 120, which isn't going to take it very long, and it still hasn't melted, then I'm going to go ahead and jump it all the way up to about 181. Alright, so we're at 120, it still hasn't melted. So I do feel confident in saying that it's not going to melt at 110. And now I'm going to set the temperature to go up to, say, 181. And since that's a pretty big jump in temperature, I'm going to set it to increase at a faster rate than normal. And right now it's in the 150s, and it's in the 160s. Oh, it looks like it's starting to melt. 169, 170, 175, 177. It started at 175 and it ended at 177. So impure, definitely, that's pretty far off from the expected melting point. But since that melting point is close to 185, then that's most likely the product that we made. For this experiment, instead of taking the IR spectrum of our product, we're actually going to take the spectrum of anise oil, our reactant. This is a really strong black licorice-y smelling liquid. It's pretty unpleasant if you don't like the smell of black licorice, which I don't. So this looks like a benzene ring, and over here there's our carbon-carbon double bonds that we would expect to see in a benzene ring, but not a lot of other stuff going on in this area, like no carbonyl. I am going to turn it around pick a few of the peaks, and then we will save this for analysis for our post lab.